Imagine a cat, a simple, everyday cat, going about its life curious and playful. Now imagine sealing this cat in a box that is completely closed off from the outside world. Inside this box there's a device that has the potential to kill the cat. But here's the twist. The device is triggered by a single atom. This atom is in a peculiar state. This atom exists in a state of both decay and non-decay simultaneously. So is the cat alive or is it dead? Or perhaps both? Welcome to the perplexing world of Schrödinger's cat, a thought experiment that challenges our understanding of reality. This thought experiment, devised by the brilliant physicist Erwin Schrödinger, isn't about animal cruelty or harming cats. It's about one of the most mind-boggling concepts in physics: quantum superposition. A concept that defies our everyday experiences. This principle states that particles, the fundamental building blocks of the universe, can exist in multiple states at once, until we observe them. When we observe them, they choose a single state. This act of observation collapses the superposition into one reality. Schrödinger's cat, trapped in its theoretical box, forces us to confront the strangeness and paradoxes of the quantum world, a world where reality is not as it seems. In our everyday world, things are either here or there, black or white, clear-cut and distinct, alive or dead, moving or still. This is the realm of classical physics, where everything has a definite state. But venture into the microscopic world of atoms and photons, and a new set of rules applies. Quantum physics, a realm where the ordinary rules of classical physics no longer hold. Quantum physics tells us that particles can be in multiple states at once, defying our everyday logic. It's like a coin spinning in the air, caught in a state of flux. It's not heads, it's not tails, it's both until it lands, existing in a superposition of states. This is what physicists call superposition, a fundamental principle of quantum mechanics. This concept is difficult to grasp because our brains are wired for the classical world, where things are either one way or another. But the universe operates by a different set of rules at the quantum level, where particles can behave in ways that seem impossible to us. And these rules have profound implications for our understanding of reality, challenging our perceptions and opening up new possibilities in science and technology. The macroscopic world around us seems to obey classical physics. Objects have definite positions and properties. A ball is either moving or at rest. A tree is either standing or has fallen. But the microscopic world of quantum mechanics is different. Particles can be in multiple states at once. Their properties are fuzzy and uncertain until measured. It's like the universe hasn't quite decided what those properties should be. The challenge for physicists is to reconcile these two seemingly contradictory pictures of reality. Where does the quantum world end and the classical world begin? And what happens at that boundary? Superposition is not just a theoretical concept. It has been experimentally verified countless times in the quantum world. We see it in the behavior of photons, electrons, and even atoms. But what about larger objects? Can a macroscopic object like a cat or a crystal also exist in a state of superposition? This is the question that has puzzled physicists for decades. Recent experiments have started to probe this boundary between the quantum and classical worlds. And the results are even stranger than we could have imagined. In a groundbreaking experiment, Swiss researchers have created a state of superposition in a macroscopic object, a tiny crystal. This crystal, though small to the naked eye, is gigantic on the quantum scale. The researchers used a special device to cool the crystal to near absolute zero. At such low temperatures, the crystal's vibrations are minimized, allowing its quantum properties to emerge. By carefully manipulating the crystal with lasers, the researchers were able to put it into a superposition of two states, vibrating and not vibrating at the same time. This is a remarkable achievement, demonstrating that superposition is not limited to the microscopic world. Section 6. Schrödinger's cat and a crystal, mirroring the paradox. The Swiss crystal experiment provides a tantalizing glimpse into the nature of reality. It suggests that the principles of quantum mechanics, such as superposition, may apply to macroscopic objects as well. Just like Schrödinger's cat, the crystal in the experiment existed in a state of both vibrating and not vibrating until it was measured. This challenges our classical intuition and raises profound questions about the role of observation in quantum mechanics. Could it be that the act of observation somehow collapses the superposition and forces the object to choose a single state? Or is there something more fundamental at play? Section 7. Bridging the Gap, Implications for Quantum Understanding. The Swiss crystal experiment has far-reaching implications for our understanding of quantum mechanics and its relationship to the classical world. It suggests that the boundary between these two realms may be fuzzier than we thought. This experiment opens up new avenues for exploring the quantum world and its potential applications. If we can control and manipulate the quantum states of macroscopic objects, it could lead to revolutionary technologies such as quantum computers and sensors. But perhaps more importantly, this experiment forces us to confront the fundamental mysteries of the universe. It reminds us that there is still so much we don't know about the nature of reality. Section 8. Quantum Leaps and Bounds, Future Research Horizons. The Swiss crystal experiment is just the beginning. Scientists around the world are now racing to create superposition states in even larger and more complex objects. Some researchers are working on putting molecules, viruses, and even tiny living organisms into superposition. Others are exploring the possibility of creating macroscopic quantum phenomena, such as quantum entanglement, in everyday objects. These experiments are pushing the boundaries of our understanding and could lead to breakthroughs that transform our world in ways we can only imagine. Section 9. The Quantum Symphony of Reality. The universe is a vast and mysterious place, filled with wonders that stretch our imagination and challenge our understanding. From the smallest particles like quarks and electrons to the largest galaxies, everything is governed by the fundamental laws of physics. These laws are the invisible threads that weave the fabric of our reality. But at the heart of it all lies the strange and wonderful world of quantum mechanics, a realm where the rules of classical physics no longer apply. Schrödinger's cat, once a thought experiment designed to illustrate the paradoxes of quantum theory, is now becoming a reality in laboratories around the world. Scientists are pushing the boundaries of what we thought possible. As we delve deeper into the quantum realm, we are discovering that the universe is even more bizarre and awe-inspiring than we ever imagined. Quantum particles can exist in multiple states at once, and they can be entangled across vast distances. The quantum symphony of reality is playing out all around us, a symphony of superposition, entanglement, and uncertainty. These phenomena are not just theoretical, they have practical applications in technology and computing. It is a symphony that we are only just beginning to understand. Each discovery opens up new questions and possibilities, leading us further into the unknown. And as we listen more closely, we are sure to discover even more wonders that will challenge our understanding of the universe and our place within it. The journey into the quantum world is just beginning, and it promises to be an exciting adventure.